The tornado is a half-mile wide, and it is heading directly toward you at 62 miles per hour. The roar is so deep and so loud that you feel it in your chest cavity before you hear it with your ears. Debris is orbiting the vortex at 270 miles per hour, sheets of metal, 2x4s, a car door. You are exactly where you chose to be. But this obsession started decades before you ever had the credentials to be this close to a monster. It started when you were 14 years old, standing in the backyard of your parents' house in Norman, Oklahoma, watching a wall cloud rotate above the wheat fields to the southwest. The base of the cloud is dark green, a color produced by sunlight filtering through hailstones suspended inside the updraft. The rotation is visible without binoculars, a slow, deliberate spin like water circling a drain. Your mother is calling you inside. You do not move. You have been obsessed with weather since you were 7, when an EF3 tornado passed 3 miles from your house in the sound. A deep, continuous roar like a freight train that never arrives shook the windows and vibrated the foundation. You watched it from the basement window. The debris cloud was brown and gray, churning at the base, and pieces of what used to be houses and barns arced through the air in trajectories that made no physical sense. You build a weather station in the backyard, a thermometer, a barometer you bought at a garage sale, a wind vane made from a tin can, and a rain gauge constructed from a 2-liter bottle. You record observations 3 times a day in a notebook: temperature, pressure, wind direction, cloud type. You learn the cloud classification system: cirrus, stratus, cumulus, cumulonimbus. You memorize the Fujita scale, F0 through F5, later updated to the enhanced Fujita scale. You know that an EF5 tornado has estimated winds above 200 miles per hour and causes total destruction of well-built structures. You apply to the University of Oklahoma, the epicenter of severe weather research. You are accepted into the School of Meteorology. Your parents drive you to campus on a Sunday in August. The sky is blue, the air is humid. You can feel the instability. You are studying atmospheric science, and you do not sleep during severe weather season. April through June, the atmosphere above the southern plains becomes a laboratory of thermodynamics. Moist air from the Gulf of Mexico collides with dry air from the Rockies under a jet stream that provides the upper-level divergence necessary for explosive storm development. This is Tornado Alley, and you are in its center. You chase your first storm at 19. A senior student with a beat-up Ford Explorer picks you up at the dorm. You drive west on I-40 toward a discrete supercell near Chickasha. The storm is visible from 40 miles away, a towering cumulonimbus that reaches 60,000 feet into the atmosphere, its anvil spreading east like a white shield. The updraft base is dark and sculpted, with a rotating wall cloud that descends from the storm's rain-free base. You park on a county road a mile south of the mesocyclone. The wind shifts. The temperature drops 15 degrees in 2 minutes. The pressure drops 3 millibars. The wall cloud tightens. A funnel descends, a white cone of condensation extending from the rotating base toward the ground. It touches. Dust spirals upward from the earth. The funnel widens, darkens, and becomes a fully condensed tornado. You stand beside the truck and watch. The tornado is a mile away. The sound is not the freight train cliché. It is a deep, vibrating hum that you feel in your sternum more than you hear. The visual is hypnotic. The tornado moves across the landscape with a deliberate intelligence, as if choosing its path. Debris orbits the funnel, sheets of metal, tree branches, objects you cannot identify rotating at speeds that exceed 150 miles per hour. It lasts 8 minutes. The funnel narrows, tilts, and dissipates, a process called roping out that looks like the tornado is being pulled back into the sky. The storm moves northeast. You stand in the silence that follows. The air smells like ozone and turned earth. You are hooked. You are terrified. These feelings are not contradictory. You graduate and join a storm-chasing research team funded by the National Science Foundation. Your role: deploy portable weather stations, pods in the path of tornadoes. The pods weigh 63 pounds each. They measure wind speed, pressure, temperature, and humidity at the surface. They are designed to survive winds of 200 miles per hour, which means they are bolted to 200 pounds of steel base plate. You drive a truck loaded with 6 pods through hail cores and rain curtains to position them in the projected path of a tornado. The path is calculated using Doppler radar velocity data and mesocyclone tracking algorithms, but the reality is rougher. You're driving on dirt roads in rural Oklahoma at 60 miles per hour in rain so heavy your wipers are useless, navigating by GPS and instinct, trying to get ahead of a storm that is moving at 45 miles per hour and accelerating. Your first deployment: a supercell near Woodward, Oklahoma. The Hook echo on radar is textbook, a classic appendage of precipitation wrapping around the mesocyclone. You deploy 3 pods along a county road at half-mile intervals. You drive away. You watch from 2 miles east. The tornado crosses the deployment line. 2 pods transmit data. The third is hit directly. The tornado picks it up, 260 pounds of steel and instruments, and carries it 400 meters. You find it in a wheat field, bent but transmitting. The data it recorded during the direct hit, winds of 167 miles per hour, a pressure drop of 54 millibars, is the most precise surface measurement of a violent tornado ever recorded at that time. Your advisor reviews the data with the team. He is not emotional about it. He says, "The data is good, the deployment was adequate. The pod placement on the third station was 12 meters east of optimal." You learn that in scientific storm chasing, the miracle is in the numbers, not the spectacle. You learn to forecast, not just to chase storms, but to predict them, to look at the morning atmospheric data and determine where, when, and how severe weather will develop. This is the intellectual core of storm chasing, understanding the atmosphere with enough precision to position yourself in the right place at the right time ahead of the storm. You study morning soundings, vertical profiles of temperature, humidity, and wind from weather balloons launched twice daily from stations across the Great Plains. You calculate CAPE, convective available potential energy, the amount of energy available for thunderstorm development. A CAPE value of 2,000 joules per kilogram is significant. 4,000 is extreme. You have chased on days with CAPE above 5,000, and the storms that develop are explosive, going from clear sky to 60,000-foot supercell in under 40 minutes. You analyze wind shear, the change in wind speed and direction with altitude. Wind shear is the ingredient that transforms an ordinary thunderstorm into a supercell and a supercell into a tornado. 0 to 6 kilometer bulk shear above 40 knots is favorable. 0 to 1 kilometer shear above 20 knots is critical. It is the low-level shear that directly contributes to tornadogenesis. You make your forecast. The highest probability for significant tornadoes today is a 50-mile corridor from Dodge City, Kansas, south-southeast to Woodward, Oklahoma. The timing is 4 to 7 p.m. You drive 300 miles to position yourself at the southern end of the risk area. At 4:17, the first tower explodes to the northwest. By 5, it is a supercell. By 5:30, it is tornado-warned. By 6, you are watching an EF4 tornado from 4 miles away, a wedge-shaped vortex a mile wide at the base, grinding across the prairie at 35 miles per hour. Your forecast was within 20 miles and 45 minutes of the event. In meteorology, this is precision. In human terms, you predicted destruction from 200 miles away using math and atmospheric physics. You become an interceptor, a chaser who closes the distance between observation and the storm itself. You no longer watch from 4 miles away. You position yourself within a mile of the tornado's path, sometimes closer, to gather data, photograph the storm structure, and document the tornado's life cycle from genesis to dissipation. The risks are real. A tornado can change direction without warning, a left-moving or right-moving deviation from the mean storm motion that puts you directly in the path. Rain-wrapped tornadoes are invisible until they are on top of you, concealed within the storm's precipitation core, detectable only by Doppler radar velocity signatures. Power lines fall across roads. Hailstones the size of softballs, falling at over 100 miles per hour, can break a windshield in a single impact. El Reno, Oklahoma. You follow a supercell that produces the widest tornado ever recorded in the United States, 2.6 miles wide at maximum extent. The tornado's outer circulation extends beyond the visible funnel, creating multiple secondary vortices, smaller tornadoes rotating within the larger circulation, that hit with EF3 to EF4 intensity. 3 experienced storm chasers are killed on this day. You survive because you made the decision to retreat south when the radar showed the tornado's forward motion shifting erratically. You drive past the damaged path the next morning. A highway overpass has been scoured to rebar. A steel-framed building is flattened. Cars are wrapped around utility poles. The debris field is 4 miles long and 2 miles wide. You stop at a Red Cross staging area and volunteer for 12 hours, handing out water and blankets to people who lost everything. You return to your truck. You sit in the cab. Your hands are steady. Your mind is not. You earn a master's degree and then a PhD in severe storms meteorology. Your dissertation is on the relationship between low-level mesocyclone intensity and tornado genesis, the question of why some supercells produce tornadoes and others, with nearly identical atmospheric environments, do not. You deploy mobile Doppler radar systems, truck-mounted units that can scan a supercell at ranges of 20 to 50 miles, and resolve the velocity structure of the mesocyclone with a precision that fixed radar sites cannot match. You operate the radar from the back of a truck, adjusting the scan elevation, the pulse repetition frequency, and the azimuthal sampling rate while the truck is parked on a dirt road a mile from a tornado. Your research produces a finding that contributes to warning science. Supercells with a strong low-level mesocyclone, rotation below 1 kilometer in altitude, that also exhibit a descending reflectivity core, a column of precipitation descending from mid-levels to the surface, are significantly more likely to produce tornadoes within 15 minutes than supercells without this signature. This gives forecasters an additional indicator for tornado warning decisions. The National Weather Service incorporates your research into its warning decision support tools. A meteorologist in a forecast office in Wichita uses your criteria during a tornado watch and issues a warning 3 minutes earlier than they would have without it. 3 minutes. A family in a mobile home park hears the warning, moves to the community shelter, and survives an EF2 tornado that destroys their home. You never meet them. You never know their names. This is the architecture of saving lives, invisible, statistical, and profoundly meaningful. You lead a research field campaign, a multi-institutional project involving 20 vehicles, 3 mobile radars, 12 pod deployment teams, 2 drone teams, and a coordination center that manages the entire operation from a mobile command vehicle. Your budget is $2.4 million over 2 storm seasons. You coordinate deployment like a military operation. Morning briefing at 8 a.m., atmospheric data review, target area identification, convoy departure time, rally points, safety protocols. The team disperses across the target area, radars positioned at flanking angles, pod teams in the projected tornado path, drone teams ready to launch into the storm's inflow region. The drones are the cutting-edge, unmanned aerial systems that fly into the storm's updraft at altitudes between 500 and 3,000 feet, measuring temperature, humidity, wind, and pressure in the critical boundary layer where tornadogenesis occurs. No manned aircraft can fly here. The drones do until the turbulence destroys them. You lose 11 drones over 2 seasons. Each one costs $8,000. Each one returns data worth immeasurably more. A field day. A violent tornado crosses your deployment array. 3 pods record surface data. 2 radars capture the mesocyclone structure from dual angles. A drone captures 3 minutes of data inside the inflow region before the turbulence snaps it in half. The combined dataset is the most comprehensive simultaneous observation of a violent tornado ever collected. You spend 2 years analyzing the data. You publish 4 papers. The papers are cited over 300 times. Citation counts are the currency of academic science. You care about them. You also care about the drone pilot who watched $12,000 of equipment get eaten by a storm and said, "The data transmitted, we're fine." You are hired by the Storm Prediction Center in Norman, Oklahoma, the national center responsible for issuing severe weather watches and outlooks for the entire United States. You sit in a room with a wall of monitors displaying satellite imagery, radar composites, surface observations, and upper air data. You are responsible for the convective outlooks, the daily forecasts that delineate areas at risk for severe thunderstorms and tornadoes. The stakes are different now. When you were in the field, your decisions affected your team. Now your decisions affect millions. An outlook that predicts a moderate risk of severe weather triggers emergency management activation across multiple states. A high risk, the most urgent category, issued fewer than 15 times per year, represents a forecast of multiple violent tornadoes expected across a large area. A high risk changes the behavior of governments, emergency services, media, and millions of citizens. You issue a high risk on a morning in late May. The atmospheric environment is as dangerous as you have ever analyzed. CAPE, exceeding 5,000 joules per kilogram, 0 to 1 kilometer shear above 30 knots. A dryline bulge that will serve as the focusing mechanism for storm initiation at approximately 4 p.m. You draw the risk area across a 150-mile corridor of central Oklahoma. At 4:12 p.m., the first supercell initiates on the dryline. By 5 p.m., 3 supercells are producing tornadoes simultaneously. By 7 p.m., an EF4 tornado crosses the southern suburbs of a major city. The damage path is 17 miles long and 3/4 of a mile wide. 24 people die. Without the warnings triggered by your outlook, refined by the local forecast offices, and disseminated through the emergency alert system, the toll would have been hundreds higher. You watch the damage surveys from your desk. The satellite imagery shows the scar across the landscape, a brown stripe through the green of late spring Oklahoma. You pull up the verification data. Your outlook was correct in location, timing, and intensity. The warnings worked. The system worked. 24 people still died. You go home and cannot eat dinner. 20 years of chasing. You have witnessed over 400 tornadoes. You have documented the evolution of severe weather science from a niche academic field to a core component of public safety infrastructure. You have seen the technology transform, from chasing by paper map and M radio to real-time mobile radar, drone swarms, and satellite imagery refreshed every minute. You have also witnessed something that changes your understanding of the work. The tornado climatology is shifting. The traditional tornado alley, the Great Plains corridor from Texas to Nebraska, is seeing a relative decrease in significant tornado activity. Meanwhile, the Southeast, Alabama, Mississippi, Tennessee, is seeing an increase. The storms in the Southeast are more dangerous. They occur more frequently at night, They are more often rain-wrapped and invisible. The population density is higher. The housing stock is more vulnerable, and the warning lead times are shorter because the mesocyclones develop faster in the high-shear, moderate Cape environments that dominate the region. You publish a paper documenting this shift. The paper generates controversy. Those who argue the shift is an artifact of improved detection, and those who argue it is real and represents a fundamental change in severe weather geography driven by climate change. Your data shows both effects are present. The detection has improved. The shift is also real. You testify before a congressional subcommittee on natural hazards. You present data showing that the average lead time for tornado warnings has increased from 7 minutes in 1990 to 14 minutes in 2025, but that the false alarm rate, the percentage of warnings that do not verify, remains above 70%. The committee asks if you can reduce the false alarm rate. You say, "We can, but it requires investment in observation networks, numerical weather prediction, and research. The atmosphere does not negotiate." You are 58 years old, 34 years of storm chasing, over 400 tornadoes observed, over 11,000 storms documented. Your research has contributed to a warning system that saves hundreds of lives per year. Your students occupy positions at universities, forecast offices, and research laboratories across 4 countries. Your body remembers every season. The permanent sunburn on your left arm from decades of resting it on the driver's side window frame. The hearing loss from hail impacts on vehicle roofs at 100 miles per hour. The chronic lower back pain from 34 years of driving 12-hour days on poorly maintained county roads. Your left knee clicks, the cartilage worn from jumping in and out of trucks on muddy shoulders. You make one last chase. A May afternoon in central Kansas. The atmosphere is loaded, 4,000 joules of Cape, 30 knots of low-level shear, a sharpening dry line west of Salina. You drive alone, no team, no radars, no pods, just you, the truck, a laptop with radar data in the sky. At 5:40 p.m., a supercell explodes on the dry line. The storm develops a rotating updraft visible from 30 miles away, a leaning tower of white cloud that catches the late afternoon sun and glows gold against a darkening sky. You position yourself on a dirt road 3 miles south of the mesocyclone center. The wall cloud descends. The rotation tightens. A funnel reaches toward the earth. It touches. Dust rises. The tornado forms a perfect slender cone of condensation against a backlit sky, illuminated by the setting sun, silent from this distance except for a low hum that you feel more than hear. You stand beside your truck. The tornado moves northeast across open farmland. No homes, no structures, just wheat and grass and the unstoppable physics of the atmosphere doing what it has done for millions of years. The tornado ropes out after 11 minutes. The storm moves away. The sky turns orange, then red, then deep purple. You stand in the silence. The air smells like rain and earth and ozone. You get in the truck. You drive east toward home. The headlights cut through the dusk. The radio plays a song you don't hear because you are thinking about the tornado, not the science, not the data, not the warnings, just the shape, the light, the sound. The raw, indifferent, overwhelming beauty of the atmosphere doing something that no human can stop, no human can control, and no human should ever stop trying to understand. You drive home. The sky darkens. The stars appear. Somewhere to the west, the atmosphere is already building the next storm. It always is.